So we have learned about work and we have learned about heat, which are both forms of energy, both ways that a system can transfer energy. However, heat tends to play a much larger role in chemical processes. In fact, there is an entire subdiscipline of chemistry called thermochemistry. It's part of the broader study of heat transfer called thermodynamics. Many chemical reactions absorb or release heat due to the energy changes associated with breaking and forming chemical bonds. So, a chemical bond is a form of potential energy. There's energy stored in that bond. In order to break that bond, you have to put energy into the system. So, breaking bonds requires energy. Whenever bonds form, energy is released. So, forming bonds releases energy and releases heat. As we've learned, the change in internal energy of a system, or the change in energy of the system, delta U, is equal to heat and work, Q plus W. It is important to understand when we study how chemical reactions consume or release energy, what we are measuring is actually the change in energy. It's nearly impossible to measure the actual total absolute value of energy in a system or even the total energy in the universe. It is, on the other hand, pretty simple to measure the change in energy of a system. This is done primarily by monitoring temperature changes. The law of conservation of energy tells us that the total amount of energy in the universe is constant. Energy cannot be created nor destroyed, only transferred from one form to another. This is also known as the first law of thermodynamics. So when the energy of a system increases, it means the energy is lost from the surroundings. So the total amount of energy in the universe stays the same. Energy gained by the system is the energy lost by the surroundings. Energy lost by the system has to go to the surroundings. Let's break this down and think about what happens when energy is gained or lost and review the signs here for these processes. Both heat and work make up the total change in energy of the system delta U. Let's think about heat first. When Q is positive, that means that heat of the system increases. So heat is entering the system, and we call this an endothermic process or an endothermic reaction. When Q is negative, heat must be exiting the system. This is called an exothermic reaction. When Q is positive, that should lead towards delta U being positive, and when Q is negative, that will lead toward delta U being negative. Work is similar. When work is positive, work is being done onto the system by the surroundings. So the surroundings is doing the work and the system is gaining the work. When work is negative, the system is doing the work on its surroundings and the surrounding is receiving the work. When both Q and W are positive, delta U of the universe also has to be positive. When both Q and W are negative, then delta U of the universe has to be negative. In the case where one of these is positive and one of these is negative, we can't predict delta U without doing the math. Sign is a very important component of problem solving for this equation and this subject matter. Always take time to think about what the sign should be and pay attention to it as you are solving problems. I'm going to stop this video here, and you should go to your worksheet number 5, post it on Canvas, and try problems number 5 and number 8. For additional practice, try problem 5.26 in your textbook. It's one of the problems in the end of the chapter, problem 5.26 in your textbook.